Title: Weak maximum principle of finite element methods for parabolic equations in polygonal domains. Abstract: This paper proves the weak maximum principle of finite element methods for parabolic equations, focusing on both semi-discretization in space and fully discrete methods with k-step backward differentiation formulae for k equals 1, 6. The study is conducted on two-dimensional general polygonal domains or three-dimensional convex polyhedral domains. The semi-discrete result is established via a dyadic decomposition argument and local energy estimates, which can handle the non-smoothness of the domain. The fully discrete result for multi-step backward differentiation formulae is proved by utilizing the solution representation via the discrete Laplace transform and the resolvent estimates, inspired by the analysis of convolutional quadrature for parabolic and fractional-order partial differential equations. Keywords: parabolic equation, finite element method, weak maximum principle, full discretization, backward differentiation formulae, Laplace transform, analytic semigroup, local energy estimate, non-smooth domain. Introduction. Maximum principle serves as a fundamental mathematical tool for the study of elliptic and parabolic partial differential equations, PDEs. The discrete counterpart of maximum principle associated to finite element methods, FEMs, has a well-established history of research and remains an active field. However, unlike its continuous counterpart, the discrete maximum principle is not an inherent property and is significantly influenced by the triangulation of the physical domain. Weak maximum principle. The weak maximum principle of the semi-discrete FEM with respect to the initial value is equivalent to the uniform boundedness of the finite element heat semigroup in L infinity, omega. This was proved in 27 for smooth domains by assuming that the partition of the domain contains curved simplices which fit the geometry of the boundary exactly. The extension to non-smooth polygonal and polyhedral domains, thus a standard triangulation with flat simplices can fit the boundary exactly, introduces more technical challenges where the elliptic regularity theory and finite element error estimates degenerate. A comprehensive solution to these issues, which emerged due to the domain's non-smoothness, was presented in a recent paper, 21. However, the weak maximum principle of the semi-discrete FEM with respect to the boundary value remains unaddressed, and this issue can't be transformed into the uniform boundedness of the semigroup in L infinity, omega. This is proved in the current paper by the representation formula via discrete Laplace transform, discrete resolvent estimates on the contour and the consistency of discrete and continuous Laplace transform together with the elliptic weak maximum principle developed in 19. Fully discrete FEM. Regarding time discretizations, the maximal LP-LQ regularity for multi-step BDF and Runge-Kutta timestepping methods, with 1 less than p, q less than infinity, was shown in 16 and 22 for semi-discretization in time and fully discrete FEMs, respectively. The authors utilized the R-boundedness concept to reduce maximal LP-LQ regularity to set inclusion, 17, theorem 1.11, which is further characterized by the concept of alpha stability. In conclusion, this paper establishes the weak maximum principle of finite element methods for parabolic equations in polygonal domains, providing insights into the discrete maximum principle and its implications for the study of elliptic and parabolic PDEs. This paper investigates the stability of the backward differentiation formula, BDF, method for parabolic equations. Specifically, it addresses the weak maximum principle of time discretizations with respect to the boundary value, which has not been previously addressed. The analysis is challenging due to the existence of boundary data, non-smoothness of the domain, and lack of astability for k-step BDF methods with k is greater than or equal to 3. The paper's two main points of analysis are: 1. Proving the weak maximum principle of the semi-discrete FEM, which requires establishing the estimate, nabla d, a u, underscore, L caret infinity, 0, t, L caret infinity, omega, is less than or equal to h, where u underscore h is the semi-discrete FEM solution, and u is the exact solution. This error estimate is non-trivial due to the lack of an approximation property for the initial value gamma underscore h, 0, gamma, 0. 2. Deriving the weak maximum principle of time discretizations by studying the representation formula of the fully discrete Fem solution U_H n in terms of the generating functions. A crucial step is eliminating a logarithmic factor introduced by the discrete convolution. This is achieved by establishing consistency between the discrete and continuous Laplace transforms, which enables the removal of the logarithmic factor. Key results include the weak maximum principle of the semi-discrete FEM, Theorem 2.1, and the fully discrete weak maximum principle of fully discrete FEMs with multi-step BDF timestepping methods. The paper also highlights the limitations of the current approach, particularly for discontinuous Galerkin timestepping methods with variable time step sizes, and discusses potential avenues for future work. Notably, the analysis relies on several key tools, including local Holder's inequality, the smoothing property of the discrete heat semigroup, and the lower bound alpha greater than 1/2, which indicates the domain's smoothness. Additionally, the paper utilizes a correspondence relation between the boundary data, stated in Lemma 5.4, to establish consistency between the discrete and continuous Laplace transforms. Here is a combined summary of pages 5 and 6. The authors introduce the backward differentiation formula, BDF, of order k, denoted as BDFk, which is used for time discretization. The generating polynomial of BDFk is defined as delta, zeta, equals underscore, j equals 0, caret k delta underscore j zeta caret j, where delta underscore j are the coefficients of the polynomial. The BDFk method is a, theta underscore k, stable, meaning that the set z element of C, 0, arg, z, less than theta underscore k, is contained in the stability region of the method. The authors assume that the starting values u underscore n caret h, n equals 0, k1, are given or computed from some other timestepping methods. The fully discrete finite element method, FEM, with BDFk timestepping method seeks u underscore n caret h element of s underscore h such that the equation 2.2 is satisfied. The authors prove a weak maximum principle for the fully discrete solution, stating that the maximum norm of the discrete solution is bounded by the maximum norm of the initial and boundary data. The authors then introduce notation and definitions for function spaces, including Sobolev spaces w caret s, q, omega, and their dual spaces h caret s, omega. They define the Bachner norm for w caret s, q, valued functions and introduce the notion of subdomains d subset of omega and spacetime subdomains q subset of 0, t, times omega. The authors define the L2 inner products on omega and the spacetime L2 inner products on q underscore t equals 0, t, times omega. They also introduce the notation for the finite element spaces S underscore H and their restrictions to subdomains D. The authors then discuss properties of the finite element spaces, including quasi-uniformity, inverse inequality, and local approximation and superapproximation properties. These properties are used to establish error estimates for the finite element method. The authors define the operator I underscore H, H underscore 0 to the power of 1, omega, right pointing arrow s underscore h, which is used to approximate functions in h underscore 0 to the power of 1, omega, by functions in s underscore h. They establish estimates for the approximation error of I underscore h and its properties, including local approximation and superapproximation. These estimates are used to establish error estimates for the fully discrete FEM. Here is a combined summary of pages 7 and 8 of the research paper. The authors establish various estimates for the finite element method, including local and global estimates for the interpolation and Ritz projection operators. Specifically, they derive the local estimate, 3.5, for alpha element of 0, 1, and v element of h, d, intersection h, omega, which implies the global estimate, 3.6, for ph and 3.7, for rh. These estimates are crucial in the analysis of the finite element method. The authors also introduce the concept of Green's functions, which are used to analyze the parabolic equation. They define the discrete delta function delta h, x and show that it decays exponentially away from x, 3.10. The Green's function g, T, x, y, is symmetric with respect to x and y and has an analytic extension to the right half-plane, satisfying the Gaussian estimate, 3.12. The authors also derived the pointwise estimate for the time derivatives of the Green's function, 3.14. Furthermore, the authors introduced the regularized Green's function gamma, which is defined as the solution of a parabolic equation with a regularized initial condition, 3.15. The finite element approximation of gamma is defined by 3.16. The regularized Green's function can be expressed in terms of the Green's function, 3.17, and satisfies the Gaussian pointwise estimate, 3.18. In the context of the weak maximum principle of semi-discrete FEM, the authors establish two parts of the result. The first part follows from the pointwise stability of the semigroup, while the second part is proved using the technique based on the dyadic decomposition and local energy estimates. The authors introduce the dyadic decomposition of the domain Q equals 0, 1 times omega, which is used to partition the domain into subdomains and present estimates of the finite element solutions in each subdomain. The authors define several sets and notations to facilitate the analysis of the Green's function and its regularized version. Specifically, they introduce the sets $q_j, x_0, $omega_j, x_0, $d_j, x_0, and their variants, which are used to decompose the domain $omega and the timespace domain $omega_t. These sets are defined in terms of the distance from a fixed point $x_0 and the time variable $t. The authors also define several norms and seminorms, including the $L² norm, the $h⁻1 norm, and the $L⁻INFTY norm, which are used to measure the regularity of functions. The authors then present three technical lemmas, which provide estimates for the Green's function and its regularized version. Lemma 4.1 establishes estimates for the $L⁻INFTY norm and the $L² norm of the Green's function and its regularized version, while Lemma 4.2 provides estimates for the $L⁻1 norm and the $L² norm of the regularized Green's function and its time derivative. Lemma 4.3 establishes the continuity of the operator $delta_h⁻1 and provides an estimate for the $L⁻1 norm of the gradient of the difference between the regularized Green's function and the Green's function. The authors also introduce a parameter $alpha$, which depends on the dimension $d$ and the convexity of the domain $omega$. This parameter is used to quantify the regularity of the Green's function and its regularized version. The authors note that the value of $alpha$ can be slightly larger than 1 in the case of a convex domain. The estimates established in these lemmas are used to analyze the regularity of the Green's function and its regularized version, and to derive bounds for the error between the numerical solution and the exact solution. The authors also note that the constants in these estimates are independent of the mesh size $h$ and the point $x_0. The proof of the stability of the constant k is outlined, leveraging the consistency and stability parts of the proof in 21, lemma 4.4. By multiplying h-1/2 in the front, the lowest powers of h in the consistency part are h alpha and h1 plus alpha minus d2, ensuring the stability of k. The stability part is also examined, revealing additional positive powers of h that guarantee the stability of k. The problem is then reduced by simplifying the notation and relaxing the dependence of the Green's functions on x0. The finite element solution A is introduced, and by substituting VH equals gamma h, s minus t, and integrating the result for t element of 0, s, an expression for A, s, x0, is derived. This expression is further manipulated by introducing WH element of L2, 0, t, she, and choosing WH equals U minus GH, ultimately yielding an expression for A, S, x0, in terms of GH and gamma H, S minus t. The solution U of the PDE problem is introduced, and by testing the first equation of 4.15 by gamma S minus t, and integrating the result for t element of 0, s, an expression for U, s. delta x0, is obtained. By subtracting this expression from 4.14, an expression for s x0 is derived, which is then bounded using the maximum principle of parabolic PDEs. The estimate, 4.21, is then introduced, and its proof is outlined in section 4.4. The local energy error estimate for finite element solutions of parabolic equations is leveraged, and the expression for partial differential t phi minus phi h qj plus d minus 1j phi minus phi h 1 qj is derived. This expression is then used to bound the term h minus 1/2 nabla f L1 dsh, ultimately yielding the desired estimate, 4.21. The proof of theorem 2.1 is then completed by substituting the estimate, 4.21, into 4.20, yielding the desired result. The estimate, 4.21, is then proved in section 4.4, leveraging the local energy error estimate for finite element solutions of parabolic equations. The authors present a detailed analysis of the error estimates for the numerical solution of a parabolic equation using a finite element method. They start by introducing the notation and the setting for the problem, including the definition of the norms and the interpolation error estimate. The main goal is to estimate the error in the L1 norm of the solution and its derivatives. The authors first consider the case where t is in the interval 0, 1, and derive several estimates for the solution and its derivatives using the basic energy estimate. These estimates are then used to bound the L1 norm of the solution and its derivatives. The authors also introduce the notation k, which represents the sum of several terms involving the solution and its derivatives. To estimate k, the authors use lemma 4.4 and set phi h equals gamma h, phi equals gamma, phi h 0 equals ph delta x0, and phi 0 equals delta x0. They then obtain two estimates, one for the L1 norm of the solution and its derivatives, and another for the L1 norm of the time derivative of the solution and its derivatives. The authors then use these estimates to bound k and derive an upper bound for the L1 norm of the solution and its derivatives. They also use the local interpolation error estimate, the exponential decay of pH delta x0, and the estimates of the regularized Green's function to derive several technical estimates. The final estimate for k is obtained by substituting the technical estimates into the expression for k. The authors conclude that the L1 norm of the solution and its derivatives can be bounded by a constant times the sum of several terms involving the solution and its derivatives. The analysis presented in this section is highly technical and relies on several advanced mathematical tools, including the finite element method, interpolation error estimates, and the theory of parabolic equations. The authors provide a detailed and rigorous analysis of the error estimates, which is essential for understanding the accuracy of the numerical solution. The estimates derived in this section are used to establish the convergence of the numerical solution to the exact solution. The authors also discuss the limitations of the analysis and the assumptions made in the derivation of the estimates. The results presented in this section are essential for understanding the behavior of the numerical solution and for developing more accurate and efficient numerical methods for solving parabolic equations. The authors provide a detailed analysis of the error estimation for the semi-discrete finite element method applied to a parabolic problem. They first introduce the notation and assumptions used throughout the paper, including the domain, the time interval, and the finite element spaces. The authors then define the semi-discrete finite element approximation and its error. In the second part of the paper, the authors focus on estimating the error in the L2 norm of the domain. They use a combination of techniques, including the energy method and the duality argument, to obtain an upper bound for the error. The bound is expressed in terms of the mesh size, the time step, and the regularity of the solution. The authors also discuss the choice of the time step and the mesh size to achieve optimal convergence rates. They show that if the time step is chosen to be proportional to the square of the mesh size, then the error in the L2 norm of the domain converges at a rate of h squared, where h is the mesh size. In the third part of the paper, the authors consider the error estimation in the H1 norm of the domain. They use a similar approach as in the second part, but with some modifications to handle the additional terms that arise in the H1 norm. The authors obtain an upper bound for the error in the H1 norm, which is expressed in terms of the mesh size, the time step, and the regularity of the solution. The authors also discuss the choice of the time step and the mesh size to achieve optimal convergence rates in the H1 norm. They show that if the time step is chosen to be proportional to the square of the mesh size, then the error in the H1 norm converges at a rate of O(h), where h is the mesh size. In the final part of the paper, the authors consider the error estimation in the L-infinity norm of the domain. They use a different approach than in the previous parts, involving the use of a cutoff function and the discrete Laplacian. The authors obtain an upper bound for the error in the L-infinity norm, which is expressed in terms of the mesh size, the time step, and the regularity of the solution. Overall, the paper provides a comprehensive analysis of the error estimation for the semi-discrete finite element method applied to a parabolic problem. The authors discuss various techniques and obtain upper bounds for the error in different norms, which can be used to achieve optimal convergence rates. The solution to equation 4.48 is expressed in terms of the semi-group at increment h, leading to equation 4.50. By applying the operator minus increment h 1/2 to both sides, equation 4.51 is obtained. This allows for the derivation of the estimate 4.52, which bounds the L2 norm of nabla RH eta t in terms of the L2 norms of nabla pH minus RH and minus increment h minus 1 gamma hs minus pH gamma s. The exponential decay estimate 4.53 and the smoothing estimates for the analytic semigroup at increment h are used to establish this result. The proof of theorem 2.1 is completed by integrating the inequality 4.52 for t element of 1 plus infinity and using Fubini's theorem and equations 3.6, 3.7. This leads to the estimate 4.54, which bounds the L1, 1 plus infinity L2 norm of nabla RH eta. By using the triangle inequality, Holder's inequality, and lemma 4.3, the estimate 4.55 is derived, which bounds the L1, 1 plus infinity W1, 1 dH norm of gamma h minus gamma. The weak maximum principle of the fully discrete FEM is proved by decomposing the solution into three parts: UNH, 1, UNH, 2, and UNH, 3, which are finite element solutions of problems 5.3, 5.4, and 5.5, respectively. The goal is to establish the estimate 5.1, which bounds the L infinity omega norm of UNH in terms of the L infinity omega norms of UNH 1, UNH 2, and UNH 3. The estimates 4.45, 4.55 imply the desired result 4.21, completing the proof of theorem 2.1. The proof of theorem 2.2 involves establishing the weak maximum principle, which is achieved by showing that the solution can be decomposed into three parts, each of which can be bounded in the desired norm. The research paper discusses the development of a novel elliptic finite element method for solving a class of elliptic problems. The method is based on a new approach that utilizes the Kronecker symbol and elliptic finite element problems to estimate various quantities. In the first part of the paper, the authors proved three estimates for the elliptic finite element problem, which are crucial for establishing the desired result in theorem 2.2. These estimates involve the L infinity norm of the solution and its derivatives, as well as the L infinity norm of the boundary data. The authors use a sector saint, which is defined as the set of complex numbers with argument between pi2 and pi2, to establish these estimates. In the second part of the paper, the authors provide the proof of the first estimate, 5.6. They define a finite element solution of an elliptic problem and use a weak maximum principle to obtain an estimate for the solution. This estimate is then used to establish the desired bound for the elliptic finite element problem. The third part of the paper focuses on the proof of the second estimate, 5.7. Here, the authors extend the definition of Gn to be 0 for certain time levels and redefine Gn1 and Gn. They also extend the definition of n to be the solution of an elliptic equation at time levels n is greater than or equal to n plus 1. By applying the resolvent estimate and the L infinity stability of pH, the authors obtained the desired bound for the elliptic finite element problem. Overall, the paper presents a new approach to solving elliptic problems using finite element methods. The authors provide detailed proofs of several key estimates that are essential for establishing the main result. This work contributes to the development of more efficient and accurate numerical methods for solving elliptic problems. The paper discusses the use of generating functions to analyze the BDFK method for solving parabolic equations. The authors first introduce the discrete elliptic equation of the generating function u(2) zeta and its solution map mh zeta. They then provide several lemmas related to the properties of the generating functions, including estimates on the inclusion of dt, e minus tau z, and the behavior of 1 minus e minus tau z, tau. These lemmas are crucial for the analysis of the BDFK method and its application to solving parabolic equations. The authors also introduce the truncated sectors saint and saint, sigma, which are used to define the contours of integration in the subsequent analysis. They fix an angle theta that satisfies certain conditions and use it to define the contours of integration. The Cauchy's integral formula is then applied to derive an expression for h(2), which involves the generating function u(2) zeta and the solution map mh zeta. The paper further deforms the contour of integration to gt theta, sigma, which consists of two parts: gt, 1 theta, sigma and gt, 2 theta, sigma. This deformation is valid due to the analyticity of the integrand and the periodicity in Im, z, with period 2 pi, tau. The authors conclude by expressing h(2) as an integral over gt theta, sigma, involving the generating function u(2) e minus tau z, and the solution map mh, e minus tau z. This expression is key to understanding the behavior of the BDFK method and its application to solving parabolic equations. The provided pages from the research paper detailed the analysis of a semi-discrete finite element method, FEM, for a time-dependent problem. The authors introduce a globally continuous piecewise smooth solution, A(2), and decompose it into two components, A(21) and A(22). They then use the Laplace transform to rewrite the semi-discrete FEM in terms of the transformed solution, U(2), and derive an equation for this transformed solution. The authors also provide a formula for the Laplace transform of a piecewise linear function, gh, which is crucial in their analysis. This formula is derived using a change of variables and straightforward calculations. The authors further estimate the Laplace transform of gh, providing bounds that are essential for their subsequent analysis. The authors then rewrite the semi-discrete FEM in terms of an operator equation involving the solution map of the homogeneous part of the equation, LH, and an operator difference, MH-LH. They bound the operator difference using the properties of theta and a previous lemma. This bound is critical for their error analysis. In summary, these pages present a detailed analysis of the semi-discrete FEM, including the decomposition of the solution, the use of Laplace transforms, and the estimation of operator differences. The authors provide a comprehensive treatment of the mathematical techniques involved and lay the groundwork for further error analysis in the paper. Here is a combined summary of pages 25 and 26. The resolvent estimate and the mapping property of mh, zeta, are used to establish the L-infinity stability of pH. This leads to the representation of the solution of equation 5.30 as u(2) z, which is given by equation 5.32. By applying the inverse Laplace transform, the solution A(2) Tn is expressed as a sum of four integrals, as shown in equation 5.33. Subtracting equation 5.33 from equation 5.23, and using the boundary condition g and h equals 0 for n is less than or equal to k1 and n is greater than or equal to n1, the difference on h(2) Tn is derived, which involves several integral terms, as shown in equation 5.34. The integral terms in equation 5.34 are further simplified by introducing functions fnh, gnh, lane h, kh, and qh, which are defined in equations 5.35 to 5.39, respectively. These functions involve contour integrals of various complex functions. Using these definitions, the L-infinity norms of Fnh, Gnh, and lane H are estimated. In particular, it is shown that a nabla dl Fnh, a nabla dl L-infinity, partial differential omega, right pointing arrow L-infinity, omega, is less than or equal to c, n cubed, and a nabla dl Gnh, a nabla dl L-infinity, partial differential omega, right pointing arrow L-infinity, omega, is less than or equal to c, n squared, where c is a constant independent of n and h. These estimates are used to bound the L-infinity norm of the sum of Fnh, Gnh, and lane H, which appears in equation 5.34. The final bound is given in equation 5.40, which shows that the L-infinity norm of the sum is bounded by a constant multiple of the maximum L-infinity norm of Gnh over k is less than or equal to n is less than or equal to n2. The paper discusses the analysis of a semi-discrete finite element method for a class of parabolic equations with non-homogeneous Newman boundary conditions. It focuses on the error estimates in the L-infinity, omega, norm for the spatially discrete solutions. The authors start by introducing the problem and its semi-discrete formulation, followed by the main results. They then provide the proof of the main theorem, which involves several lemmas and inequalities. The first part of the proof involves bounding the L-infinity, omega, norm of the discrete solution A2, t, using the L-infinity, partial differential omega, norm of the discrete solution A2, s, and the discrete initial data gh. This is achieved through a series of inequalities involving integrals over certain contours in the complex plane. The second part of the proof involves bounding the L-infinity, omega, norm of the discrete solution A2, tn-1, using the L-infinity, partial differential omega, norm of the discrete solution A2, s, and the discrete initial data gh. This also involves a series of inequalities involving integrals over certain contours in the complex plane. Finally, the authors prove the error estimate in the L-infinity, omega, norm for the spatially discrete solutions by combining the previous results and using the triangle inequality and theorem 2.1. In addition, the paper discusses the proof of another error estimate for the spatially discrete solutions, which involves solving for UK element of Shay at the time tk and using the triangle inequality and theorem 2.1 to obtain the desired bound. Overall, the paper provides a detailed analysis of the error estimates for the semi-discrete finite element method applied to a class of parabolic equations with non-homogeneous Newman boundary conditions. Here is a combined summary of pages 29 and 30 of the research paper. The authors establish the weak maximum principle for semi-discrete and fully discrete finite element methods with k-step BDF timestepping, where k equals 1, 6, using generating polynomials and the discrete inverse Laplace transform. The analysis requires a uniform timestep size. The elliptic equation for the generating function is derived, and its solution is represented using Cauchy's integral formula. The authors then prove the weak maximum principle by estimating the L-infinity norm of the solution, applying the resolvent estimate and the L-infinity stability of pH. The authors also discuss the limitations of their approach, noting that it cannot be readily extended to k-step BDF methods or other single-step methods with variable time-step sizes. However, they suggest that the discrete semigroup estimates in 20 can be applied to the discontinuous Galerkin (DG) timestepping method with possibly variable step sizes, yielding a weak maximum principle with an additional logarithmic factor depending on the maximal step size tau. In the appendix, the authors provide a proof for the weak maximum principle of DG 0 with variable step sizes, using the discrete semigroup estimates in 20. The general DG K can be treated similarly by using the approach from 20. The proof involves defining the spacetime finite element space of degree 0 in time and degree r is greater than or equal to 1 in space, and applying the DG 0 method to the homogeneous parabolic equation. The authors then state a proposition on discrete semigroup estimates in LP, omega, which is used to establish the weak maximum principle. Overall, the authors contribute to the development of numerical methods for parabolic equations, providing a comprehensive analysis of the weak maximum principle for various finite element methods with different time-stepping schemes. The paper discusses the discrete Galerkin method, DG, for solving parabolic equations with a focus on the weak maximum principle. The authors introduce a DG, solution to a parabolic equation with a non-zero right-hand side, which satisfies a specific equation involving projections and finite element approximations. They then establish the weak maximum principle for the DG, method, providing an estimate for the discrete solution in terms of the finite element approximation of the boundary data. To prove the weak maximum principle, the authors define a discrete harmonic extension and its difference with the discrete solution. They use discrete integration by parts and properties of a rational function to obtain an estimate for the discrete solution. This estimate involves terms related to the elliptic theory and the discrete harmonic extension. The authors further simplify this estimate using the properties of the rational function and the elliptic theory, eventually arriving at the desired bound. The weak maximum principle is crucial for understanding the behavior of the discrete solution and its relation to the continuous problem. It provides a way to control the discrete solution in terms of the boundary data, which is essential for error analysis and convergence studies. The paper's results contribute to the development of more efficient and accurate numerical methods for solving parabolic equations, particularly those with non-zero right-hand sides. The proof of the discrete maximum principle for finite element solutions of parabolic equations is concluded, establishing the stability and analyticity of the numerical method. The result is obtained by combining the triangle inequality with the assumption of a minimum time step size, yielding an estimate of the error in the L-infinity norm. The final bound is expressed in terms of the logarithm of the time step size and the mesh size, demonstrating the optimal convergence rate of the method. The references cited in the paper provide a comprehensive overview of the existing literature on finite element methods for parabolic equations, including works on discrete maximal regularity, stability, and analyticity. The authors draw on a range of sources, from classical texts on heat kernels and spectral theory to recent papers on finite element methods for stochastic partial differential equations. The list of references highlights the contributions of various researchers to the field, including the development of discrete maximal regularity theory, the analysis of finite element methods for parabolic equations, and the study of stability and convergence properties. The citations also reflect the interdisciplinary nature of the research, with references to works in mathematics, numerical analysis, and scientific computing. The final page of the paper presents additional references, including works on finite element methods for elliptic and parabolic equations, as well as papers on numerical methods for ordinary differential equations. These citations provide further context for the research and demonstrate the author's engagement with the broader scientific community. Throughout the paper, the authors employ a range of mathematical techniques, including functional analysis, partial differential equations, and numerical analysis. The use of precise mathematical language and notation ensures that the results are presented in a clear and rigorous manner, making the paper accessible to experts in the field.